Hey there, everyone. Today we're going to look at, or begin to look at, what are known as rational exponents and radical expressions. Now, there's a lot packed into that little phrase, but let me just go back. I used the word exponent at the same time that I used the word radical. Now, I think you guys know what exponents are, although we're going to go a little deeper with exponents. And, well, we've been starting to talk about radicals. Here's the deal. They are connected. Exponents and radicals, they definitely go together. I also use the word rational exponent. Perhaps you're wondering, what's a rational exponent? Well, that means it's going to be a fraction exponent. Now, we've got some new stuff to talk about, but don't worry, we'll figure it out. I'd like to actually start with some introductory comments on these, what are known as higher order radicals. Now, a higher order radical just means that it's no longer a square root. Notice we have here a cube root, and we also have a fourth root. It's of a higher order. I'm going to actually flip over to another page just to make it a little bit easier to talk about this. So we have the same problems. And, well, what does this mean? What does it mean to think of the cube root of 8? Well, honestly, it means that you're looking for three numbers that multiply to be 8. And, oh, by the way, they have to be the same three numbers. Can you think of three numbers that multiply to be 8? Yeah, you should be thinking of 2 times 2 times 2. Now, if you aren't able to think of that, you're going to start to be able, because we're going to be thinking this way. We're looking for higher order radicals. So if the number 2 multiplied together 3 times is equal to 8, well, that means that the cube root of 8 is equal to 2. The cube root of 8 is equal to 2. What about a fourth root? Yeah, that's definitely of a higher order. Now we're looking for 4 numbers that multiply. They have to be the same 4 numbers, and they multiply to be 81. Now again, some of this takes just like a little trial and error. Sometimes you get error before you get the trial. Sometimes you try and you hit it, but are you thinking about 4 numbers that multiply? Now, if you know the number 3, you eventually would know that if I take 4 of them, they're going to equal 81. What does that mean? That means the fourth root of 81 is equal to 3. Higher order. Now, there are more cube roots. There are more cube roots that we can talk about than just the cube root of 8. So if we go back to cube roots, I want you guys to start to realize that, well, there's other numbers that we would say are perfect. What would be another number that's perfect? Well, you'd have to realize that if you choose 3 3s, that means that the cube root of 27 would be perfect. Of course, that would equal 3. But what if I choose 3 4s? Well, that's going to give me another perfect cube root. Of course, the cube root of 64 is equal to 4. We're not going to fill in all of them, but the point is that we need to be able to start thinking about other perfect numbers involving cubes. What if we kind of do a root? Now remember, a root, that's the same as a radical sign. So here I'm doing the fourth root, but what if I do a root and I do an exponent? How am I going to do a root and an exponent? Well, we're going to have to do them both, not at the same time, but we're going to have to kind of do them both with an order of operations. So the first thing I'm going to do is I'm going to do the fourth root. I'm looking for 4 numbers that give me 16. Whoa, that's going to get me all the way back to the number 2. So that's because 2 times 2 times 2 times 2 is 16, right? So this gives me 2, but then I have this exponent. Yeah, this exponent that we don't want to forget about here, this exponent of 3. So 2 to the 3, oh yeah, well that would be like 2 times 2 times 2. Now if you feel like you're kind of going backwards and forwards, you're right, because a radical kind of makes you go backwards. it gives you backwards back to the number 2. But an exponent obviously makes us go forwards, and so I go forwards and I get to the number 8. Eventually, you guys are going to make sense of something like this. Now, something like this is known as a rational exponent. A rational exponent is an exponent that's a fraction. Oh my goodness, how can I have an exponent that's a fraction? Well, actually, it's not too bad. It just means that we have a root and we have a power. And you guys are going to learn that the root is going to always be the denominator. The power is going, or the power is going to come from the numerator. And so I end up with really the 4th root of 16 to the 3rd power. The 4th root of 16 to the 3rd power. Now forgive me, I wanted to put this power on the outside. So I've got the 4th root of 16. Well, I can do that. That would be like trying to find 4 numbers that give you 16. Oh, we just did that. That is the number 4. And then the power of 3, well, oh, whoops, it's not the number 4. Sorry, I'm getting a little excited. It's the number 2. We just did that. The 4th root of 16 is the number 2. And then that's going to be to the 3rd power. Oh, wait a minute, we just did that. It's actually the same problem from above. And so our final answer comes out to be 8. This was called a rational exponent because basically we had an exponent that was a fraction. And when you have a rational exponent, you're going to learn that we can rewrite the problem. We can rewrite the problem as a radical. Here we have the 4th root and a power to the 3rd power. Now, let's go back to your paper here. And what I'd like to do now is encourage you guys to check out some problems. We're actually going to check out the problems that are in this left-hand column, these 2 left-hand columns, you might say here. And you're going to check these problems out with your calculator. Yes, I want you to get out a calculator, and I want you to see what your calculator has to say about these problems. Now, this is an important part of the lesson, meaning that you need to pause the video. Yep, you want to pause the video, get out a calculator, and see if you can punch in some of these expressions. Now, if you're like, okay, I'll try it, but how do I know if I'm doing it right? Okay, just push play, and I'll show you, the first one, and then pause the video again and see if you can get the next one. So get out your calculator, pause the video, and see if you can figure out how to punch in 4 to the 1/2, 64 to the 1/3, and then the rest of them. All right, I see you. You still need to get out that calculator. Now, if you did get out your calculator and you just kind of want to check the first one, that is a good idea, because what I need to do 4 to the 1/2 power is understand how my calculator's exponent key works, as well as the fraction button. For most of you, the exponent key is going to be this caret top key down here. Let's get that to show up a little better. So I punch 4 caret top, and then I definitely want to use these parentheses around the fraction just to make sure that the calculator understands that the entire exponent is 1/2. And it looks like you get 2. So you can do an exponent that is a fraction. Try the next one. Try 64 to the 1/3. Not too hard to do. Just use your calculator's exponent button. Remember that exponent button is this caret top button. Punch that sucker in there and you get 64 to the 1/3. Now, the whole point behind this is that you guys understand that you can have an exponent that's a fraction, and it actually comes out to be an actual number. Try the rest of them. Make sure you can punch those in. Eight to the 2/3 comes out to be 4. And a little bit dark, but 16 to the 1/4 comes out to be 2. I wonder what's going on here. I wonder what this 4 really represents. 16 to the 1 4? I wonder how we're ending up with the number 2 as our final answer here. Well, that's the next part of the lesson. But how about a negative exponent? What happens if you pop in there a negative exponent? Well, first of all, you can. You can do 25 to the negative 1/2. You get this little decimal. I'm going to share with you that this decimal, and if you have the ability, you can change it to a fraction on your calculator, or I'm going to share with you that the fraction for this would be 1/5. And you can write it as 1/5 if you would like. Let's go back now. I'd like to do a little bit more directing you to what in the world is going on with your calculator and these expressions. If you look at the first one, I've got 4 to the 1/2 power. Now, 4 to the 1/2 power, you should notice that 1 is the numerator, 2 is the denominator, and if I go over here, we find out that we can actually rewrite this problem. We can rewrite this problem such that the denominator ends up to be the root. We call that a square root. And the numerator, well, the numerator, that ends up to be the power. Looks like what I really have here is like the square root of 4. Well, yeah, the square root of 4, that's equal to 2. It's the same answer. That's because it's the same problem. 64 to the 1/3. Numerator is 3. Yeah, sorry, numerator is 1. I meant the denominator is 3. If the if the denominator is 3, that we notice is the same as the root. If the numerator is 1, that's the same as the power. It's like I have 64 to the first power, and then I'm going to do the cube root. Now remember, the cube root of 64 is like 3 numbers that give you 64. 3 numbers that give you 64? That's right, it's 4. That's the same answer. That's because it's the same problem. Are you catching on? Let's do it the other way. The denominator. It looks like the denominator is ending up to be the root. In this problem, the 3rd root. Looks like the numerator is ending up to be the power. In this problem, it'd be like a square. So I get 8 squared. I get 8 squared, which is 64. And then, the 3rd root of 64. Well, we just did that up above. It's 3 numbers that give you 64. Comes out to be 4. Now, you can actually do this problem in the other order. No, it doesn't mean you change the numbers. It just means that you do the radical or the root first. Now, if I do the root first, that'd be like trying to do the 3rd root of 8. The 3rd root of 8 is going to be the number 2 because 2, 2, 2 equals 8. I can do the power second, and, well, look, 2 squared is equal to 4. Do you see it working with the next one? Do you see how we're going to end up using 4 as the root, and we're going to end up using 1 as the power? Yep, comes out to be 2. Comes out to be the same answer. Now, this last one is kind of interesting because it's got a negative. It's got a negative, but look carefully. First of all, I still have a denominator. The denominator is the root, so it's like the square root. The numerator is the power. Now, it happens to be a negative power, and you guys are going to learn eventually, but we're going to mix it in today, that a negative power is going to flip a problem over. And it flips the problem over, so now it's, instead of the square root of 25 over 1, it's 1 over. It's 1 over the square root of 25. And so we end up being able to think of this as 1 over 5. 1 over 5. So what's going on here? Well, to say it one more time, we have what's known as rational exponents. Now, I don't want this to just be words, like gobbledygook words. Rational exponents, kids, rational exponents are exponents that are fractions. So we have rational exponents. Well, they are the same as powers. Now the powers are the numerator, so the same as powers, and radicals. Radicals end up being the denominator. Rational exponents. Well, it's the next thing, and they can be thought of as separately powers and radicals. Here, let's break it down. If I have a to the m over n power, a to the m over n, so I have a rational exponent. M is the power. M is the power, which kind of rhymes with flower. Well, it doesn't kind of rhyme, it does, but it makes you think of a flower. N is the root, like the bottom of the flower. So the top is the power, the bottom is the root. Flower power. You can rewrite this as n root. You can rewrite this as the n root and the m power. Now the whole point here is that there are two ways to basically describe the same type of problem. Okay, so just relax. There's two ways. They both can give us the same answer. What we want to be able to do now is we want to be able to kind of think in both ways. So if I have 5 to the 3/4 power, then I should be able to, and a lot of times kids will first think about the root. Now that would be like the 4th root. So they'll think about the root of 5 and then to the 3rd power. So 3 is the power that goes on 25. Now, if you're kind of looking at this and saying, what do you do with it? Well, you do what you can. I think we can do 5 to the 3rd power. That'd be like 555. That's 125. But I don't know if I can find 4 numbers that give me 125. Not 4 numbers that are integers. So we can just stop there. We can kind of rewrite this as either the 4th root of 5 to the 3rd power, or we can even simplify it to the 4th root of 125. Do you think you can rewrite 54 to the 1/3? Can you rewrite it? A lot of times people do the root first. It's the 3rd root of 54 to the 1st power. Yeah, you don't really need that 1st power because that's not going to change it. Can I find 3 numbers that give me 54? Not that are integers. So we're not going to worry about trying to get that on the calculator right now. It's more just realizing that you can rewrite the problem. How about 125 to the 2/3? Part of today is hopefully realizing that this statement, 125 to the 2/3, well, it actually means something. Something that you guys can understand. Are you rewriting it or are you just waiting? Rewrite it, please. You should be doing the root first. That's typically what we do. That way you have a space to put the 2 as the power. Now, a problem like this can actually be, and as all the problems can be, rewritten or also written with the power just on the outside. Let's put the power on the outside because guess what? I can actually find 3 numbers that give me 125. Yep, there are 3 numbers that give me 125. 5 times 5 times 5. So now that I wrote this as 5, or was able to simplify it to be 5, then I can do 5 squared. Yeah, I can do 5 squared. You can do 5 squared. That equals 25. So it's an interesting problem because, well, honestly, because you can. You can break it down. you can break it down into 3 numbers that give you 125, and then it simplifies the whole way to 25. What do we have here? Just a place to kind of rewrite what it is that's going on. If you have a to the m over n, if you have a to the m over n, that's the same as the nth root of a to the m. And as I just showed in the previous problem, it is also okay to think of this as the whole thing to the m. And maybe we'll rewrite it that way just for something different. But m is definitely the power, flower power, and the n is the root. One more thing with this concept, and it's basically going in the reverse direction. Now, going in the reverse direction, or excuse me, not going in the reverse direction, but being able to work with some other expressions. So here, it really doesn't matter that it's 4c minus d. What really matters is that you understand that the 5, as it was on the front, it is on the back, it's the root. The 2, it's the power. And so if I was going to rewrite this problem in radical form, well, it would have to be such that I have this entire quantity squared. Unless I wanted to write it like this, just to be honest, that is kind of nice too. Both of them are the same. Uh-oh, a negative exponent. I told you guys that we would talk a little bit about negative exponents, but we're definitely going to be doing more with them. But listen, a negative exponent, it just means that you end up flipping your expression. So I think you guys can flip that. You just get 2x to the third. You don't really need to write it over 1 because that's the same as just 2x to the third. Now, just so you know, the exponent is now positive 1/2. Don't flip the exponent. Don't flip the exponent, just make it positive. That's what happens. The exponent flips to be positive, but, well, that's right. I have a denominator, and a denominator is the same as a root, and I have a numerator, but the numerator is 1, so it's not really going to make any difference if I put the number 1 here or if I put the number 1 here. The truth is I don't need either of those 1s. I just need the square root. Oh yeah, the square root. So I don't even need that little 2. Now that's one thing I haven't really said today, but it's definitely true that the square root is the assumed root. So we don't record that 2, at least we don't have to record, again, the 2 that is assumed to be that root. See if you can write this in radical form. I know, I gave you a negative exponent. Just think of this as 5x over 1. Because you want to flip and make it 1 over 5x. Can you keep going? Can you write this in radical form? Four is the root. It's the 4th root. Yep, it's the 4th root of 1 over 5x. You can have a fraction in there. And then it's all to the 5th power. We'll write it this way with 5 out on the outside. Now, I thought we were going to do some problems backwards. So as a final piece of this, let's write the answer as a rational exponent. Remember, rational means a fraction. You guys know what an exponent is. So we're going to write these as fraction exponents. Well, listen, it's just going backwards. 4 is the root, 3 is the power, flower power, so that goes up top, 4 goes down below, c to the 3/4. Doesn't get too much easier than that, but it can get harder. Man, we have a fraction. Now listen, when you have a fraction, you have to anticipate that there's going to be a negative exponent. There's going to be a negative exponent, but it's still a flower power. What I mean is that the exponent is still going to be 6 over 3 because, well, that's how it works. 6 is the exponent, and or excuse me, 6 is the numerator and 3 is the denominator. Now, I've got this fraction, I've got this like 1 over. I don't want it to be a fraction. I want it to just be 5x. But how do I make it 5x so it's not a fraction? Well, I need to have a negative exponent. So, tricky problem, but basically this negative exponent of negative 6 over 3 is going to be able to, it's going to be able to turn my problem back into what I started with. Interesting though, my exponent could certainly be simplified to be negative 2, couldn't it? Yeah, I can just write this as 5x and negative 2. Okay, again, negative exponents, they cause the base to flip, but they can also cause me to go backwards and sort of flip it back up. Try one. Interesting problem. Is it missing something? Perhaps. Maybe you want to think that it's to the power of 1. Does that make it a little easier to do? Flour, numerator, flour power, denominator's the root. 10 to the 1/6 power. 10 to the 1/6 power. I basically rewrote the problem as a rational exponent. Well, kind of a different lesson today for sure, but we're starting to expose you guys to the next concept with roots and powers. So as we often say, try the homework. Okay, it's the same thing. It kind of has all the different variety of problems that we've done today. We will definitely be using these concepts as we continue talking about roots and radicals.